Good morning students, welcome to your chemistry class. Let us further discuss the chapter chemical bonding and molecular structure. And in this, today our topic of discussion will be molecular orbital theory. Now to understand molecular orbital theory, first we should know what is atomic orbital theory. So what is atomic orbital theory? First, let us consider an atom. Now in an atom, there will be orbitals. Every orbital contains 2 electrons that we know and they have opposite spins. So when we are considering an atomic orbital, they have 2 electrons with opposite spin. Now what is an orbital? It is a 3-dimensional space in an orbit where the electron finding probability is maximum. Now further, what will happen? One atomic orbital is going to combine with another atomic orbital and this will give rise to molecular orbital of the molecule. So atomic orbital theory combines with another atom's atomic orbital theory and this will give rise to molecular orbital theory. Like one nitrogen combines with another nitrogen to form N2, that is nitrogen molecule. N, the nitrogen atom, they will be like atomic orbitals, and the N2 which is formed, there that atomic orbitals will be modified into molecular orbitals. Now what is the significance of molecular orbital theory? The first one is that it will suggest us that a molecule or ion is possible or not. Supposing we talk about H, that is hydrogen, combines with hydrogen to form H2. Now why this is possible? Because one hydrogen has one S1 and the other one is having one S1. So both are going to combine together and molecular orbitals will be formed. But if we consider helium molecule, is He2 possible? We know that He2 is not possible because one helium has 2 electrons in its s orbital. Another one is also having 2. It's completely filled. So therefore He2 is not possible. The second thing that we can find from molecular orbital theory is that we can calculate the bond order in a molecule. Now what is this bond order basically? So with the help of molecular orbital theory, we can calculate the number of bonds present in a molecule. If we are predicting that oxygen molecule is possible, then what will be the bond order? That means how many numbers of bond will be present in oxygen molecule. So we can calculate bond order from molecular orbital theory. Next, we can predict the magnetic behavior of the complex, that the compound is paramagnetic or diamagnetic. When a compound or a molecule will be called as a paramagnetic compound when there is unpaired electron present in its orbital. But if all the electrons are paired up, then that particular molecule will be known as diamagnetic molecule. That means there will be no effect of magnetic field on that molecule. Now when atomic orbitals combine, they combine and give 2 sets of orbital. One is bonding molecular orbital and one is anti-bonding molecular orbital. The bonding molecular orbital has less energy and it provides maximum stability. And the anti-bonding orbital is higher up in the energy and it is represented with a star. It signifies that it is an anti-bonding molecular orbital. The orbitals which want the combination to be successful are known as bonding orbitals, and the orbitals that do not want the combination to be successful are anti-bonding molecular orbitals. Now let us take example of H2 molecule. Here one H is going to combine with another H. So these are the atomic orbitals of hydrogen atom. Now we know that in one S, atomic number of hydrogen is 1. So therefore there will be 1 electron. In another hydrogen also there will be 1 electron. Now one orbital can consist of 2 electrons. So when they combine, then in the bonding molecular orbital 2 electrons will be there. Now with this we can calculate bond order as well. So the formula to calculate bond order is Nb minus Na, that is number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2. Now in this case we have 2 electrons in the bonding molecular orbital, but we have no electron in the anti-bonding, and it is divided by 2. This gives me 2 by 2, which is equals to 1. So therefore, when H2 molecule is considered, we write it as H dash H, that is only one bond is formed. Now let us take example of helium, that is Hg2, that we were discussing initially. Now when we consider helium, the atomic number of helium is 2, that means the configuration will be 1s2. So one atom of helium will have 2 electrons, the other one is also having 2 electrons. Now when they combine in the bonding molecular orbital, maximum capacity is to accommodate 2 electrons. The 2 electrons that are left, they are going to go in the anti-bonding molecular orbitals. Now by using this formula, let us calculate bond order for the same. That is 2 electrons in bonding minus 2 electrons in anti-bonding divided by 2. That becomes 0 by 2, which is equals to 0. Therefore, no bond is possible in He2. So therefore, this molecule is not possible. Likewise, we can draw molecular orbital diagram of different molecules, but we should take into consideration that the total number of electrons present in them is below 14 or above 14. Supposing when we consider carbon, if I want C2 to be formed, that means total there will be 12 electrons. I will be following this arrangement for species which are having below 14 electrons, and the species that are having above 14 electrons, for them we are going to use this arrangement. Now we know that p orbital has 3 orbitals, so therefore when we mix those s and p orbitals, there is an arrangement difference that occurs, due to which below 14 will show a different arrangement and the above 14 electron arrangement will be having a different molecular orbital. For this, you should remember that the atom that has less than 14 electrons, the arrangement will be first 2 pi orbitals will be drawn, then the sigma orbital, and this will be pi star and sigma star. Here also that arrangement is same, pi star and sigma star, but down what happens is sigma is first and pi is afterwards. To remember this arrangement, you can remember the number 2 1 2 1. Here you can remember 1 2 2 1, so that it is easy for remembering it. Now let us consider fluorine molecule. Now in fluorine molecule, one fluorine atom has atomic number 9, so the electronic configuration is 1s2, 2s2 and 2p5. In this case, we have not drawn 1s2 orbitals because every atom is going to have this. So instead of drawing it in a molecular orbital, we will rather put the k star while writing the electronic configuration. Now what orbitals that we have to draw is, we have to draw 2s and 2p orbitals. Now p consists of 3 orbitals. Accordingly, we have arranged the electrons. First, we have to singly fill the electrons, then we have to pair them up. Since 5 electrons are there, accordingly we have drawn the electrons in their respective orbitals, and then the filling is going to take place likewise. Now after all this, when we have drawn the molecular orbital diagram, we have to write the electronic configuration of F2 molecule. According to the orbitals involved, we are going to write the electronic configuration. Now we have not drawn here 1s, but if it is there, it will be represented as sigma 1s2 and sigma star 1s2, right? So according to that, we will start writing the electronic configuration of F2 molecule. So it is sigma 1s2, that is, it consists of 2 electrons, sigma star 1s2, then it is sigma 2s2, sigma star 2s2, that is, they are consisting of 2 electrons. Then comes sigma 2pz2, pi 2px2, pi 2py2, pi star 2px2, pi star 2py2. This is the electronic configuration. Till here we have written where the maximum filling of electron has taken place. Now after doing this, we will count the number of electron in our bonding orbitals and in the anti-bonding orbitals. So when we count, the NB value and NA value you are going to get. Now for NB, that will bonding electrons, you have 10 in number, and when we calculate the anti-bonding, it is 4, plus 4, that is 8. So let us calculate now the bond order for the same. So bond order is equals to NB minus NA divided by 2, which comes out to be 10 minus 8 divided by 2. So when we calculate this, we will get 2 by 2, which is equals to 1. So fluorine, when we consider fluorine F2, we consider it has single bond because the bond order comes out to be 1. So this is how we are going to write the electronic configuration and calculate the bond order for fluorine molecule, and rest all will be also done in the same manner. Thank you so much, students.